Good morning, students. In this class, we will start new course VLSI design. Nowadays, VLSI design is most popular course and which provides more number of job opportunities to the ECE students. It provides very good number of job opportunities to the ECE students. When we will find the VLSI chip applications in many fields, right from the our real-time applications and to industry applications and automobile applications. In different type of applications in our daily routines also we will use VLSI chips. In our mobiles, in our laptops, in our PCs, in our PCs, in our cars, in our aircraft, in everywhere we will use this VLSI chips. At the end of the session or course, at the end of the class, we will be able to know the fundamentals of VLSI, know the different types of mass transfer, understand the operation of the mass transfer. First, we will see the introduction about the VLSI. VLSI stands for Very Large Scale Integration in the process of creating an integrated IC by combining thousands of transistors into a single chip. After invention of transistor in 1960, VLSI began in the 1970s when complex semiconductor and communication technologies were being developed. The microprocessor in computers is an example for VLSI device. An integrated circuit IC is a small semiconductor-based electronic device consisting of fabricated transistors, resistors, and capacitors. Integrated circuits are the building blocks of most electronic devices and equipment. An integrated circuit is also known as a chip or microchip. Before going to the VLSI course, first we have to see the Moore's law. What is the statement of Moore's law? Moore's law is a term used to refer the observation made by Gordon Moore in 1965 that the number of transistors in a dense integrated IC doubles about every 2 years. If you see the graph, right from the 71 to the 96 to till date, this is the x-axis indicates the year and y-axis indicates the number of transistors or transistor count on a single IC. According to the Moore's law, the number of transistors per chip doubles for every 2 years. Okay, so the number of transistors doubles for every 2 years. So the starting process 4004, 80808, 8080 till now Pentium 2 processor. Now we have Pentium 4 dual core, different generation processors are there. So this is the statement of Moore's law. What is the statement of Moore's law? For every 2 years, the number of transistors per chip will become double. Now, IC technology. IC technology is broadly classified into different technologies: bipolar, CMOS, BiCMOS, SOI means silicon on insulator, silicon germanium, gallium arsenide. So these are the different type of technologies available for design and IC. But out of these all technologies, the CMOS technology is a preferred technology. Why a CMOS technology is preferred? Because it has low power dissipation, high packaging density, scaled we can scale down more easily. Then nothing but the size of the IC can be reduced, fully restored logic levels, approximately equal rise and fall time. Rise and fall times are equal. So these are the advantages of CMOS. That's why we prefer CMOS technology over the other technologies for the VLSI chip design. Next, we will see different scales of integration. We have small scale integration, medium scale integration, large scale integration, very large scale integration, ultra large scale integration, giant scale integration. What is small scale integration? The small scale integration introduced in 1960, MSI in 1967, LSI in 1972, VLSI in 1978, and the ULSA and GLSA are right now in research stage and in developing stage. The small scale integration is nothing but the technology was developed by integrating the number of transistors are 1 to 100 on a single chip. Examples are gates, flip-flops, and op-amps. Small circuits. Middle-scale integration. That is in 1967, the technology was developed by integrating the number of transistors of 100 to 1000. Okay, on a single chip. Examples are counters, multiplexers. Examples are counters, multiplexers, adders, 4-bit microprocessor, etc. Large scale integration (LSI). It is invented in 1972. The technology was developed by integrating the number of transistors around 1000 to 10,000 on a single chip. Example is 8-bit microprocessor, ROM and RAM. VLSI. The technology was developed integrating the number of transistors of 10,000 to 1 million on a single chip. Example are 16 to 32-bit microprocessor, peripherals, complementary high MOS. ULSI, the technology was developed by integrating the number of transistors of 1 million to 10 millions on a single chip. Example are special purpose processor. Chain scale integration, the technology was developed by integrating the number of transistors of above 10 millions on a single chip. Example are embedded system on chip. Basic MOS transistor. Transistors are main building blocks in electronics and logic circuits where they are used for switching purpose and amplification purpose. MOSFET is a type of FET whose gate is electrically isolated by using an insulating layer. Therefore, it is also known as IGFET, insulated gate field effect transistor. MOSFET or metal oxide semiconductor field effect transistor is a type of FET having four terminals, namely drain, gate, source, and body or substrate. The body terminal is shorted with the source terminal, leaving a total of three working terminals just like any other transistor. The MOSFET conducts currents between its source and drain through a path called a channel. The width of the channel is controlled by the voltage at the gate terminal. MOSFET is a voltage control device whose output depends upon gate voltage. The metal oxide gate is electrical isolation from channel using a thin layer of silicon dioxide. It increases its input impedance significantly in the range of megaohms, 10 to the power of 6. Therefore, MOSFET does not have any input current. The MOSFET has mainly two types, depletion MOSFET or enhancement mode MOSFET. The depletion mode MOSFET is also known as normally on, and the enhancement MOSFET is known as normally off. The depletion mode is called as normally on because they have a built-in channel during manufacturing. Applying gate voltage reduces the channel width, switching off the MOSFET. While the EMOS is also known as normally off because there is no channel during the fabrication, but it is induced by applying the gate voltage. Some MOSFET is divided into enhancement mode and depletion mode. Again, enhancement mode is divided into P channel MOSFET, N channel MOSFET. Depletion mode is divided into P channel MOSFET and N channel MOSFET. The P channel MOSFET again has, this is the diagram of depletion mode MOSFET. This is the diagram of enhancement mode of MOSFET. Clearly observe that there is a channel between the source and drain. It is formed at the time of fabrication. There is no channel between the source and drain. That is the difference between the depletion mode and enhancement mode. This is the N channel. Previously, you have seen the P channel. This is the N channel. There is a channel between the source and drain. In depletion mode, no channel between the source and drain in enhancement mode. Operation of N channel E MOSFET. We will take an example for NMOS enhancement mode. The N channel E MOSFET has a no channel during the fabrication. The channel is induced by application of voltage across the gate. N-channel MOSFET will not conduct current between its source and drain terminal when the VGS is equal to 0 volts because there is no channel to allow the current flow. Applying the positive voltage VGS to the gate produces an electric field beneath the gate layer. It results in attracting the electrons from the P substrate and pushing back holes away from the insulating layer. A channel is induced which allows the current between the source and drain. The VGS at which the channel is induced is called the threshold voltage, and increasing the voltage above VTH causes the enhancing the channel width. This is the operation. Generally, a MOSFET is operates in three regions. They are cutoff region, non-saturation region, and saturation region. When VGS greater than VTH, VDS is equal to 0, the channel is formed but no current flows between drain and source. This region is called as cutoff region. Second case, when VGS greater than VT and VDS is less than VGS minus VTH. This VGS minus VTH is called as effective gate voltage. Then the region is known as non-saturation region or linear region. When the drain current increases linearly with VDS, the VDS is increased, the drain side becomes more reverse biased, hence more depletion region towards the drain end, and the channel starts to pinch off. This is called pinch off point. VGS greater than VTH and VDS is greater than or equal to VGS minus VTH. This region is called saturation region where the drain current remains almost constant. As the drain voltage is increased further beyond VGS minus VTH, the pinch off point starts to move from drain and to the source end. Even if the VDS is increased more and more, the increased voltage gets dropped in the depletion region, leading to the constant current. The typical threshold voltage for an enhancement mode transistor is given as 0.2 VDD. So this is the NMOS enhancement mode transistor. So this is the source, this is the drain region, and this region is known as depletion region. You all know that when a P-type material and N-type material are joined, a depletion region is formed at the junction. And this is the SiO2, which is act as insulator, which will separate the source and drain or isolate the source and drain. Above that we have a polysilicon. Okay, the polysilicon is used for gate purpose, on which we apply a positive voltage to on the transistor. On the gate, we will apply the positive voltage to on the transistor, and the source is always connected to the substrate. We have to maintain that is always 0. So there are different notations are used for the indication of different layers. Metal, this is the metal layer, polysilicon, oxide, N diffusion, P substrate, N substrate, and this is the depletion region. So this is the diagram of MOSFET. Okay, above the gate we apply the VGS. Okay, for the drain we apply the VDS. This is VGS. This is the VDS. When we apply positive VGS here, when we apply positive VGS here, on one side of the gate, the positive voltage is accumulated. On the other side, it will repel the positive voltage or nothing but holes in the p-type substrate which are magnetic array and attract magnetic array electrons from p substrate to the other side of the SiO2. So these signs indicate the accumulation of electrons. Here the charge inversion will takes place. The charge inversion will takes place. Because of the charge inversion, a channel is created between the source and drain. After the channel is created between the source and drain, we will increase the VDS value. When we apply the VDS value, the electrons will flow from source to drain. The current is indicated as IDS, that is from drain to source. These are the different regions of operations. This is when VDS greater than VT and when VGS greater than VT and VDS is 0 volts, the channel is formed between the source and drain. When VGS greater than VT, VDS less than VGS minus VT, the channel is pinching off, starting the pinching off. When VGS is greater than VT, VDS greater than VGS minus VT, the channel is already pinched off. Okay. So after the pinched off of the channel, the a constant current will be passed in between source and drain. This is the cutoff region operation. This is non-saturation region operation. This is the saturation region operation. MOSFET region operation that we have already discussed. Transistors act like insulator or a conductor based on the very small signal. The MOSFET, like any other transistor, also operates in three regions: cutoff region, saturation region, or linear or ohmic region. In this region, the MOSFET remains turned on and there is no drain current ID. When the MOSFET is used as switch, it utilizes the region as off state or open-ended of a switch. Saturation region. In this saturation region, the MOSFET allows a constant current between the source and drain. It acts on the on state or closed state of the switch. The MOSFET is fully on, allowing maximum current ID through it. Linear or ohmic region. In this region, the MOSFET offers constant resistance that is controlled by the voltage level VGS. The drain current ID increases with the level of the VGS. Therefore, the region is used for amplification. Operating modes, we already see cutoff mode, linear mode, saturation mode. Okay, in cutoff mode, VGS is less than VTH, VGS is greater than VTH, VDS is less than VGS minus VTH, saturation is VGS greater than VTH, VDS greater than or equal to VGS minus VTH. So these are the different type of MOSFETs. So for an N-channel MOSFET, VGS is less than 0, it is off. VGS is equal to 0, it is off. VGS greater than 0, it is on. For an N-channel MOSFET, VGS less than 0, off. VGS is equal to 0, on. VGS greater than is equal to 0, it is on. P-channel MOSFET, VGS less than 0, on. VGS is equal to 0, off. VGS greater than or equal to off. P-channel depletion region, VGS less than 0, on. So these are the operations of different type of transistors for different type of VGS. You can look into this table. Now, what is the difference between the MOSFET and BJT? Why we prefer MOSFET for the designing of VLSI circuits than BJT? There are two types of MOSFET and they are named as N-type or P-type. BJT is two types, they are named as NP and PNP. MOSFET is a voltage control device, BJT is a current control device. The input resistance of MOSFET is high, the input resistance of BJT is low. Used in high current applications, used in low current applications. These are the difference between MOSFET and BJT. Thank you.